Alright, welcome back. So we are going to keep working on operational amplifiers and with more types of examples. And those will be the videos for a little while. Because, operational amplifiers are very, I think the correct word for it is versatile. Like you can use it in many ways. And I would like to explore with you those types of many ways, to better understand how to calculate it and how to do it. And don't worry, eventually we get to the point where you use capacitors. And from what I understand is when you use a capacitor inside an op amplifier, it actually works as a filter. And of course, in op amplifiers, we don't always have to use DC power. We can, DC sources, we can also use AC sources. I won't go over the rules again because, we're just going to go and work through the exercises. And here it's one of them. What's different from this exercise compared to the others is that here is the amplifier and is controlled by a switch that has 2 points, point A and B, and based on the switch we can determine is it either on point A or it's on point B. Now what we have to do is to divide the voltage output from point B with the voltage output from point A. And how do we do that? Well, it's very simple. Calculate for both positions. Alright, so let's get started. Let me get another color. So this is red, this is blue, and this is black. What color? Oh, this is black as well. No, let's see. There you go. This one is blue. Okay, that's good then. Alright, so let's start with the first one. Let's start with position A. So at position A. Alright, and now let's use the red one for position A. So let's say the switch is in position A. That means that A will be equal with 2 volts, and this one, there's no current going through these 2 points, as you know, and this one would be V1, and the minus will be equal with the same number that V1 is equal to. Alright, okay, so what do we need to do? Well, first step would be to calculate V out, and V out, let's write the formula for it, will be something along the lines of this one. So, and also let's actually put this on because B is not connected to anything, so this one will be seen as ground, so that will be 0 volts. Okay, so we have this one point V1 here, and we have two voltages going through it, 2 currents going through it, and 1 current coming on this direction. So we can say this one will be I1, and this one will be I2, and then this one here will be the I total, I. Alright, and we can make this into a formula because I1 and I2 are coming inside the node. We can say these are the positives, and we can say that I is the negative. So we can make the formula I is equal with I1 plus I2. Alright, okay, and now we simply have to calculate these values. So let's start with I1. I1 is this one here, and we apply Kirchhoff's current law, so that will be 10 volts minus V1 divided by 2K. So that will be 10V minus V1 divided by 10K plus, and now I2. I2 again, it's V1 in here, but it's got 0 volts because B isn't connected to nothing, so basically this is ground. So that will be 0 minus V1 divided by 2K. So that will be 0 minus V1 divided by 2K. And that will be equal with I. And I will be V1 minus V out divided by 2K. So that will be V1 minus V out divided by 2K. Now the problem that we have is that we have 2 unknowns now. We have V1 as an unknown, and we also have V out as an unknown. And what we can do is determine the value of V1. But how do we do this? Well, we can apply the voltage divider rule because there's only one current going through here, I, and there are 2 volts coming through. So then we can say that V1 is equal to, let me put this one a bit higher, 2 volts times 2K, the resistance here, over 2K plus 2K. and that will simply be equal with surprisingly enough with just 1. And now we just need to replace the value v1 with 1. So then it will be 10v minus 1v over 10k plus 0 minus 1 over 2k equal with 1 minus v out over 2k. So now we shouldn't have any problems finding the value of v out. Actually, let me put like v out a, v out a, v out a, there we go. Yeah, that should be good, because we tried to find the voltage output for when it's in position A. Okay, now this will be equal, therefore this will be 9 over, wait a second, it's 2k, it's not 10k. I don't know where I got this value from, sorry about that. 2k here, 2k there, and this one is 2k. Okay, sorry about that. That'll be 9 over 2k plus, no, it will be minus, because there's a minus 1 over 2k equal with 1 over 2k minus VOA over 2k. All of them have the value of 2k, so I can simplify it further, or we can simply calculate it by doing the division. So then therefore for milliamps it's equal with 5 times 10 to the minus 4 minus VOA over 2k. Therefore minus VOA over 2k, it's equal with 3.5 milliamps. Therefore minus VOA, it's equal with 7. Therefore VO, it's equal with minus 7. And that's the answer. No, wait, VOA, it's equal with minus 7. Alright, so that's the first one in position A. Now let's take the blue pen and move the switch to position B. We'll move the, yeah, this purple actually is not blue. Okay, we move it to position B, then B becomes 2 volts and A becomes 0 volts, because this A will become the ground. Alright, the V1 stays the same. No, I mean the dots V1 stays the same, but the value of V1, this value here, we also change. There are 0 volts at this end and there are 0 volts at this end as well. That means when you apply current divider rule, no, voltage divider rule, then you'll get 0 volts in here as well. So this will change to 0 volts, which will make into a completely different new formula. Alright, then let me put this a bit lower. I should have enough space. So let's separate it, make it separate. There you go. So at position B, V1, it's equal to 0. Okay, and the formula is basically the same. It will be current I1, and that's 10 minus V1 over 2k, but this time for current I2 it will be 2 volts minus 0 volts over 2k, because the switch and our point B has got the voltage. So if you rewrite this one, it will be something like this: 10 minus 0 over 2k plus 2 minus 0 over 2k is equal with 0 minus VO over 2k. Therefore that will be 10 over 2k plus 2 over 2k equal with minus VO over 2k. Okay, therefore that will be 5 milliamps plus 1 milliamp equal with minus VO over 2k, and therefore 6 milliamps will be equal with minus VO over 2k. Therefore minus VO will be equal with 12. Therefore VO is equal with minus 12. Alright, this is a mistake in my part. I should put like the value B here. I mean, I guess you understand this is implying that it's VOB, but just in case, you know, even when you do an exam, you should like put the values, and even if you forget to put them while you do it, at least put them at the end, as like I do. It's better than not put them at all. So now let's go back to the problem. It's asking us to divide VOB by VOA. So both of them are negatives, so they have to make a positive division. So VOB divided by VOA, that's equal with minus 12 divided by minus 7, that's equal with 12 over 7, and that will be equal with 1.7 volts. And that's the answer for this question, for this type, for this amplifier with a switch. Remember, switches sometimes can be tricky, because if it's a dual switch like this one that has position A and position B, remember that when position B is activated, then position A will be 0 volts, it will become a ground, and when position A is activated, it's got 2 volts inside of it, position B becomes a ground. Don't forget that it's a ground. So when it's in position A, don't just ignore this part of the circuit, even though it's got 0 volts through it. Because again, remember that in the amplifiers, this node here, the common node, will have voltage going through it anyway. Okay, so thank you for watching this one. I'll pause here and then we're going to go to the next exercise. Okay, so here's the next exercise, and this one is a lot simpler compared to the previous one, which was this one here. This one, why I did it is because you might think it's confusing, because it's very differently how that it's in a very different position. Instead of being a resistance going through here and you need to find V out, the other resistance is going downwards, and it's R2 and R3. Now the tricky thing that you need to learn is not really tricky, is something important, is that this V out output is not always you need to understand that output here is just a wire, is not really a component, which means that it can be kind of moved. For example, and you'll see in a second why I like this problem and why it's a bit tricky, it's what's the difference between VO being at this point and VO being at this point here, where there isn't any difference between those 2 points, because they are just in a wire, there's no resistance, there is no different paths, no nothing. But what if I say it's here, that V out it's equal to V out here, and that's true as well. Again, because yeah, there's a splitting here, but there isn't really any resistance, so there is no current coming through here in a way. Now what if I move this point here, and now we can see where I'm going with it. Basically this VO, sometimes you need to look at it and be careful with it. Because you can place it in a position where it helps you solve a problem, because by having VO here and a long wire here, it will make it a lot more complicated, but by moving V out at this point here makes the problem a lot simpler. You know why? Because you just need to find the voltage at this point, which means that when you cut the current through here and we determine that V1 is at this point, you also know that V1 will be at this point here. Okay, and then wait a second, my brother called me. Sorry about that. My brother was hungry, so I gave him some bacon. Anyway, so yeah, as I was saying, it's important to know this VO, because this will make it a lot simpler. Because what this actually did was transform the whole circuit. So instead of seeing a circuit like this one, we can look at it as a circuit as this. So let me quickly redraw it. Hopefully you will understand what I'm doing here. And again, remember, it's okay to like redraw a diagram and redo it, because it's part of understanding the circuit and knowing how to solve it. Instead of putting this type of V in, we can also just put a circle like we usually do and just name it V in. And R1 is going through V in, so this be resistor R1. And here's the split at point V1 at the common point, and we know the split happens around here because this is V1, so it splits at V1. And at this junction, this is VO, so we can say that RL it's in here, connected to ground. Now R3 is here, which is kind of like RL, R load. This is R1, this is R2, R1, and this will be the ground. And then we have it. We simplify the circuit a lot by doing so. By just discovering that VO is equal with the VO here, we can actually just redo this circuit in this form, which is easier for us to understand and see. I usually apply quite often this technique, or like just trying to redraw a circuit into a way that's more comfortable for me, that's easier to understand for me. Because to be honest, like sometimes circuits are complicated only because of the way they are drawn, because we are used to see them as rectangular, and you see a few problems about this. We are used to see them as rectangular, so when we see different shapes or different forms, we don't really understand them. Alright, so V1 is going to ground, so there will be 0 volts, so this will be 0 volts. And we basically just apply our usual Kirchhoff's current law. So this will be current I, this will be current I. So then V in minus V1 divided by R. So V in minus V1 divided by R will be equal with V1 minus V out divided by R2. V1 minus V out divided by R2. See, we don't even need R3 in here. Okay, therefore V in minus 0 will be over R1 will be equal with 0 minus V out over R2. Therefore, V in over R1 is equal with minus V out over R2. Okay, we can divide by R1 on, no, wait, we can multiply by R1 on both sides. So this will be V in equal with let's see, V out times R1 over R2, and now we can divide by V out. So then therefore V in over V out is equal with R1 over R2, and it's a minus as well here, so I shouldn't forget the minus. Okay, but we don't want the V in over V out. This is wrong, you know, we want V out over V in. That's usually the way that we do it for the gain. So we can just flip them around. We can say that therefore V out over V in it's equal to minus R2 over R1. So this is the answer for our problem. It's a simple inverter circuit, you know, the very basic kind. Anyway, yeah, so that's the answer for the question for this type of circuit. Again, I find it interesting because you can sometimes move the V out in such a position that's helping you solve the problem. Okay, I'll pause here. Okay, this one is another simple one, but it's playing more on the idea of nodal analysis really. And why would I say that? Well, we both know that it's not going through here, but this one it's V2. And this is one of the rare cases that we can use both the V1 and V2 to create the formula. So this dot here, this one will be equal with V2 here. Now, what we do is this. So in other analysis, you know, there are multiple currents coming in, and the law is like currents come in, but also there are currents that come out. All right. So what we do is basically this. We say that there's a current I1 coming in from this direction. I should call this one I2, and this one, because this is Beyonce, makes more sense. And this one is a current I1 coming inside. We have those two that come inside, and then you have this current here that's coming outside called I. Okay, now, no wait. Is it like that? So V1 minus V2 over R. Yeah, just give me a second, because it doesn't really make a lot of logical sense. No, I think it's correct this way. Yeah, because we need a current to come out in this direction to go to V out, so that'll be the total current, and these two currents are coming inside. So I think this is the correct way. I just said it's simple, but no, it's because like in my notes it's a bit more different. In my notes I have this one as the primary current, and then these two are the secondary current, and I don't really know why, but yeah, let's keep going. So then I1 plus I2 will be equal with I. Therefore I1 it's equal with V1 minus V2 divided by R, plus, and then I2 will simply be 0 minus V2 divided by I2R. 0 minus V2 divided by 2R. Then I will be equal with V2 minus V out divided by 3R. V2 minus V out divided by 3R. Alright, now what do we have to do? Well, we have to get them to a common factor. So we need to multiply this one by 3, and we will need to multiply this one by 1.5. Okay, so we get the same R. Then we'll get therefore 3v1 minus 3v2 over 3r plus, right, this will be a minus 1.5 v2 over 3r equal with v2 minus v out over 3r. Therefore we can get rid of these r's, so we'll get 3v1 minus 3v2 minus 1.5 v2, which will be equal with v2 minus v out. Okay, so minus 3 v2 with minus 1.5 v2, that will give us therefore 3v1 minus 4.5 v2 will be equal with v2 minus v out. Therefore 3v1, we move this v2, positive v2 to the negative, and the other side as negative, so that will be 3v1 minus 5.5 v2 will be equal with minus v out. But we don't really want the v out to be a negative because that's asking us for the positive v out. Okay. Oops, my battery died, so I guess this will be all the recording for today. Anyway, let's keep going because there was only one more step. So then v out will be equal with, we switch the sign, so that will be a positive 5.5 v2 minus 3 v1. Now I got the exact same result as my notes, which is a little bit strange because in my notes, and I'll show you here like this, the way I did it was the other way around. The current I1 was going in this direction, we're going in the outside direction, and then this current I was going in this direction. But somehow, by even inverting those two currents, I still get the correct answer somehow, but I'm not sure how, but I still do. It just shows like how solid nodal analysis and Kirchhoff's current law is. Like even though you like reverse two of the signs, as long as two of them are coming in and one of them is coming out, it just gives you the same answer. But anyway, forget about what I read in red. Remember that the ones that I did in black are the correct one, because there's I1 coming through here, I2 coming through here in node 2, and then I is coming out. This is the more logical way to do it. I don't know why I did it in the other way when I was writing the notes. Maybe I just wrote them wrong. Who knows? I don't, that's for sure. Alright, so thank you for watching. Don't worry, there are more videos in this episode, I think. Anyway, bye bye. Okay, so let's keep going. Now, this is a double op-amplifier connection, but I like the normal buffer amplifier that we usually do, you know, with nothing here or just the same resistance. This one is got a voltage divider here, and we are going to need to find out V out. Alright, so how do we start? Well, first of all, again, just put crosses where there's no current going through it, so we don't make the mistake, and let's start from this point here. Now, this is the plus pin, so this one will become V, let's call it V prime. So then this one will be equal with V prime as well. So then V prime will be equal with 2 volts. Alright, and what we need to do next is that we need to calculate this point here, V01. And of course we are going to calculate this point here so that we know what voltage is coming inside here. Okay, And the reason why we want to know what voltage is coming here to this pin is because this is the positive side, it's the plus side, so this one will be the kind of V prime for this one. So this pin will be equal with, let's say at this point, VO1. So we need to know VO1 to be able to calculate it here and then find the final V out. Alright, so then we will calculate V out here. First of all, there is the current here, so V prime is equal to 2 volts. Also, you may say maybe it's not 2 volts because it's a resistor and isn't current going through here, and the answer is no, there is no current going through here because current can't go through the pin. So there is zero current going through the 2k ohm resistor, so it just stays 2 volts. There is no voltage drop in here, that's why it's equal to 2 volts. Okay, so this is the current I coming on this side to this node, and then this is the current I coming out of the node. So then minus 4V, the input, minus 2V divided by 2K will be equal with 2V minus VO1 divided by 2K. It's got the same denominator, and therefore minus 4V minus 2V will be equal with 2V minus VO1. Therefore, minus and minus, that's the minus, will be minus 6V, and that will be equal to 2V minus VO1, and therefore minus VO1 will be equal with minus 8V. And we take out the negative sign, so we get VO1 will be equal with 8 volts. So in VO1 at this point there are 8 volts coming through, and then there will be 8 volts at this point as well then. Alright, so we solved the first half of the circuit. Now we need to solve the second half, where the input is 8 volts through this pin, making this node here be equal with 8 volts, and now we just need to calculate the voltage out. Again, it's very simple as long as you do it step by step. And remember, you can do this to apply this to like 3 amplifiers or even 4 or so on, as long as you know the steps and you know to separate the nodes and the voltages. It's okay. So then here it's 0 volts. So the current, there's no current going through here, so the current will travel this way, and we can see that V out, it's also at this point here, V out. So we can still apply Kirchhoff if we wish to, because there will be a current here I, and there will be a current through here I. Remember, there is no current going through here. Alright, so then 0 minus 8 volts divided by 2K, it's equal with 8 volts minus V out divided by 2K. Alright, therefore minus 8 will be equal with 8 minus V out, and then therefore we move it to the other side, so minus 16 will be equal with minus V out, and therefore we just take out the negative signs, so VO or V out, or whatever you want to call it, will be equal with 16. Oops, sorry, you didn't see the last equation, but it's self-explanatory. Therefore minus 16 is equal with minus V out, therefore we take the negative sign also, V out will be equal with 16 volts. And that's our answer right here. Okay, and I mean, like, we'll do double amplifiers, but not all of them will be as simple as this one. This is an example on how to calculate it. But anyway, I'll pause here and then we are going to go to the next exercise. Okay, now this one, it's a little bit more complicated and a little bit more longer than the other ones, because we want to find the V out, but V out, it's right in between this how do we call it, rhomb circuit, I guess. And remember, it's kind of like coming out of the output as well, and we got these two currents here as well, these two pins as well. Okay, so how I would tackle this problem? Well, first of all, there's no current going through here, there's no current going through here. You know, again, basic first step. And second step is that this one is at the point at the positive pin, so this will be kind of like V prime. Therefore this point here, this node here, it's equal to 2 volts. All right. Okay, next step, that would be that we need to first look at the circuit and see what we can determine. So that's what I determine first. The next thing we determine is, because there's no current going through here, to this wire here, then I will simply go in this direction, something like this. Okay, and it will go to here, and here it will split. So let me do it in red actually. So here it will split into currents. To split in this direction, current I1, and this direction, current I2. Alright. Okay, and because this is kind of an opening, so no current is coming through here, then through this resistor again it's still I2, and through this resistor it's I1. Okay, but another important thing is that there are multiple nodes as well. So this node here, there'll be V1, the voltage coming inside. Then this node here, this will be V2, the voltage output after all the current went to the resistors. Okay, and I think they should be actually the same because they are in parallel, shouldn't they? Let me check a second. Because I think I saw that. No, they are different. Okay, it makes sense why they are different. There's still the voltage output in here. Anyway, so just remember that it's a current I1, it's coming in this direction through here, and current I2 is going in that direction like this. Okay, we don't really need to worry about this side here because we just want to find the minus V out, V in. But also remember there are other two nodes here with a different voltage, which this one will call it, this will call it VA, we'll call this one, and we'll call this one VB. Okay, okay. So this is everything we can annotate and determine from here. The reason why we need also these two voltages is because theoretically V out will be equal with, we can assume that the current maybe goes in this way, depends. So let's assume, I'll do like in blue, let's assume the current goes in this way, then V out will be equal with VA minus VB. Alright, because this one will be the predominant voltage, this voltage will be bigger than the voltage here in VB, and if that's true, then what's left between VA and VB, that will be the voltage VO. Okay, but again this is assuming that VA is the bigger one, is the bigger voltage. Okay, I know the answer idea for this one, which one is the bigger voltage, but again you don't know when you first start, so you assume one of them is. And remember, if there's no really wrong way to assume, because if you get a positive voltage, then you made the correct assumption. If you get a negative voltage, that means that the polarity actually goes in the other way around, you know, instead of coming in this direction, if it's negative, then it goes, then VB will be bigger than VA, so to go in this direction. Okay, okay, so let's start with the first step, and that will be to try to find this voltage V1 here. Okay, and how do we do this? Well, again, we just apply Kirchhoff, because we have one current going through here, and the same current will go out to here to V1. So this is 0 volts, so you can say that 0 minus 2V divided by 100 is equal with 2 minus V1 divided by 200. Alright, so we multiply this one by 2, therefore minus 4 over 200 will be equal with 2 minus V1 over 200, therefore minus 4 is equal with 2 minus V1, therefore we move to the other side as a minus. Minus 6 will be equal with minus V1, and we make both of them positive. So let me actually write it in blue so we remember this is an important value. V1 will be simply equal with 6. Alright, now we found V1, which is equal with 6 volts. Now what we can find out, what we can calculate next, it's these 2 points VA and VB. The problem though is that we don't know the current split between I1 and I2. If all the resistors have the same value, then the current split will be simple, because it will be half and half. But because these values aren't the same, they are different resistances, then the current split is different. Okay, so also I think we should calculate the current as well. So current I, this current here coming in, that will be equal with the voltage 6 divided by the resistance 200. Oh no, wait, it will be equal with 2 minus 6 divided by 200, and that will be equal with, that will be 4 over 200. Well, that should be like 0, that should be 30 milliamps, shouldn't it? Let me check. So 2 minus 6, 2 minus 6 all divided by 200, 0.02, that will be minus 20 actually. Okay, now I wonder, did I, yes, I think I might have done the wrong calculation, didn't I? So 2 volts are coming in, 6 are coming out. Okay, let's try with the other one. If I'm wrong, this one should be equal with 20 milliamps as well. So then change this on to 100 and change this on to 0 minus 2. Yeah, it is. Okay, I got it wrong in my notes then. Good thing that I checked again, or else they'll be the wrong answers. Alright, so that'll be equal to minus 20 milliamps. In my notes, I have minus 30 milliamps. Okay, the reason it's minus also because it's minus 4, so yeah, that's a negative one. I got minus 30 milliamps somehow, and yeah, we'll have to like recalculate together now, but it's fine because it doesn't make that much of a difference. I mean, it's in calculation, it's not really hard to like recalculate. You just plug them in the calculator. Alright, so now we need to like find the total resistance through I1 and I2. Okay, so RT in I1 will be equal with, so I1 goes through these two resistors, so that will be 100 plus 500, that will be simply 600, so 100 plus 500, that will be equal to 600 ohms. Okay, our total in I2 will be equal with 500 again, but this time it's added by 250. That will be 500 plus 250, and that will be equal with 750 ohms. Alright, now we need to calculate the current division. We applied the current divider rule to find I1. Let's start with I1 because we need to find both of them, so let's start with I1. So by applying current division, I1 will be equal with, then we say the opposite total resistance, which will be I2, so be equal to 750 multiplied by the total current I divided by 600 plus 750. That will be equal with, here, so we do 750 times 20, yeah, let's put the minus here, 20 times 10 to the minus 3 over 600 plus 750. That would be equal with, that's only, is it, yeah, it's 11, okay, 11, yeah, 11.11, that would be equal to minus 11.11 milliamps. Okay, so that's the current I1. Now we need to calculate for the current I2, but that's really simple because the formula here is that it ends up here with the I again. So it simply be equal with I1 because it's coming through this node, I2 because it's coming through this node, equal with I because I is coming out of the node. So then I will be equal with I1 plus I2. Therefore, I2 is equal with I minus I1. Therefore, minus 20 milliamps minus 11.11 milliamps equal with I2. Okay. Now, that would be like what, 8.99, wouldn't it? No, 8.89. So 20 minus 11.11, yeah, 8.89. So I2 would be equal with 8.89 milliamps, and it's a minus, yes. Okay. All right. So we have also the I2 current. Now what we need to do is we need to find the voltages VA and VB. And again, it's a very simple way to do so because it's only one current going through and we know the value of that one current, so we can apply the voltage divider rule. Okay, let's start the page. So then let me see here on my notes. So I did two methods to calculate okay, so then I1 it's equal with V1 minus VA over 100 ohms. Oh, okay, so I apply Kirchhoff's law. Again, another way to calculate is by simply applying Kirchhoff's law because I1 is coming in through this direction and it's another I1 coming through this direction. So then, okay, so it's like a different way to apply Kirchhoff's law. So we know that in Kirchhoff's law, you know, the current coming in, it's equal to the current coming out, yeah? The way I did it is like, I said that I1 it's equal to minus V1 minus VA over 100. Basically what I did, I said I1 it's equal to I1. And the way that I did it is because I1 here, it's also equal with V1 minus VA divided by the 100 ohms, okay? So then you'll see in a second why this is that. So because we know I1 as being minus 16.67 milliamps, it's equal with, and then we can say that V1 because 6 will be 6 minus VA over 100. Now let me, I guess because like now when I look at it, because I did this exercise 2 days ago, now when I look at it I'm like, oh okay, we have only one current going through it, we have two resistors, you can apply voltage as you call the voltage rule, voltage divider rule. But apparently, again, there are many ways to solve it, but apparently I used a made up Kirchhoff's current law. I mean, it is Kirchhoff's current law because it's logical that I1 is equal with I1, but still it's a bit strange the way I did it. Anyway, let me turn the page so I know the answer to the calculation. Therefore, minus 16.67. Alright. No, wait. This. Ah, my god. I'm sorry. It's using the old numbers. I1. You may not like wonder where I got this value. Okay. So I1 is minus 11.11. Okay. because I said like last time, I got 13 milliamps on my notes, so minus 11.11 milliamps. Okay, therefore we need to do 11.11 milliamps times 100, so 11.11 that's in the minus 3 times 100, that'll be equal with 1.111. Okay, so 1.111 amps, it's equal to 6 minus VA. Okay, so we do the answer minus 6, that give us therefore minus 4.889 minus VA. Yeah, it's equal with minus VA, therefore VA will be equal with 4.889 volts. Alright, so we have one of the numbers here, which is, now it's again 4.889. okay, so that would be 4.889 volts. Alright, for VA. So I have half of it. Now we need to find the other half, which is VB here, and that's using the current I2. Alright, so I2 it's equal with, and let's see here, that'll be 6 minus VB over 50 ohms. So that'll be 6 minus VB over 500 ohms. Okay, and that'll be equal with, therefore I2, that was 8.89, yeah, minus 8.89 equal with 6 minus VB over 500. This is milli, is it milli? Yeah, it is milliamps. Okay, so then we just multiply it, so 8.89 that's in the minus 3 multiplied by 500, that will be equal to 4.445. okay, 4.445 equal with 6 minus VB, therefore, and this is still a minus, therefore minus VB would be equal with, wait a second, this this one will be a minus as well, that means it goes to this side, so that will be, okay, that will be 7 point, oh my god, I'm sorry, that will be 7.111. Alright, now you see why I usually solve the problems beforehand and why I take notes, so I can avoid situations like this one where I do a miscalculation and then I realize it later on. And again, I did it because I forgot to put the sign in front of it. Okay, so this is not 4.889, it's 7.11. okay, 7.11, okay, 111, sorry, volts. Alright, and minus VB, that would be minus 10.445, so therefore VB will be equal with 10.445. My god, it's such a small difference. In my notes I got something along the lines of 5 volts for like V out, but this one is got a really small gain because this is only 10.445, okay, 10.445 volts on this side here. So we got the value for VA, we got the value for VB. Now what we need to do is to just calculate the total. Alright, so then V out will be equal with VA minus VB. That one will be equal with, I need to like correct it here, so it's 7.111. That will be equal with 7.111 minus 10.445, and that will be equal with, so then 7.111 minus 10.445, that's equal to minus 3.334. Alright, volts. So it's a negative value. That means that the direction that I assumed it's wrong, actually it goes in the opposite direction, so the arrow should be in this direction here because the current will flow in that direction actually. Alright, and that's how we solve the problem. Sorry that I got it mixed up a little bit doing it, but again, it's because I got in my notes I wasn't equal with, actually let me write it here, I wasn't equal with 20 milliamps, it was equal with 30 milliamps, and I had the calculations, the numbers for when it's 30 milliamps. Yeah, it's a good thing that I solved them beforehand because I can catch the mistake while doing it. I'm still wondering why I got only 20 milliamps. I guess the way I solved it, I guess I saw because 4 over 200, I think that's 0.03, wasn't it? No, yeah. So let's check actually. 4 divided by 200. No, that's still 0.02. Where did I get the 30 milliamps from? Anyway, it's fine. We managed to like see the mistake, so yeah. I'm not really an expert with it, with this type of circuit anyway. And so this was this exercise here. Hopefully you understand how to do it. And remember, if I have advice, a little bit of advice about how to solve this, first of all, make sure your calculations are correct. I mean, you already noticed that, but more importantly, remember to notate everything you can notate, you know, because if you started without putting the 2 volts in here, without notating this one as V1, V2, and this one VA, VB, if you just saw the simple row diagram with no notation on it, then it will get very confusing. We wouldn't really know if it's current going through here, through the V out, if it's only one current going this way, or what formulas we can apply inside of it. Anyway, yeah, thanks for watching, and I'll see you in the next exercise.